Hi, and welcome to the presentation of my game engine for Boku. After quite some indecisiveness and several failed attempts, I chose to create my engine in C++ as a console application. Still, I wanted the board to look good, so I created an ASCII art version to print it to the console, which you can see here on the right. Also, all the inputs are text-based, meaning that the user has to type out his move. But more on this will be shown in the demonstration at the end of the video. All moves are handled as single strings, and capture moves are handled as one single move that simultaneously places and takes a piece from the board. Doing captures in one move instead of two has quite a few advantages down the line. The board itself is represented by a 10x10 array of hexagon objects. As the game board only has 80 tiles on it, 20 of these hexagons are deemed invalid. The validity of a hexagon is set in a designated class variable, together with a label like A1 or E5 and a status. This status can be 0 if the tile is empty, 1 if player 1 has a piece on there, 2 if player 2 has a piece on there, 3 if this tile is blocked for player 1 so he can't place a piece there, or 4 if this is blocked for player 2. The gameboard class also is responsible for everything that's board related, like generating moves, determining the winner, or providing an evaluation value. All of the functions you can see here in the code, but here and in the coming slides I will only provide the code as an overview of the implementation and I will not explain it in more detail. And as you can see, for the hexagon class there's also a coloring option, which will be discussed during the demonstration later. The evaluation of the current game board is determined like this. For each aspect that benefits player 1, some number is added, and for those benefiting player 2, the same number is subtracted. These aspects and their corresponding values are as follows. We get 100,000 points if the player wins, and therefore it's the highest value. We get 20 points for each piece that the player has on the board. We add a bonus of 0 to 8 points, depending on how close this piece is to the center of the board. And we subtract 5 times this distance for blocked tiles. So a tile that is blocked in the center is worse than one that's blocked at the edge. Also, there's a bonus for chains of pieces, where a chain of 2 gets 2 bonus points, a chain of 3 gets 7 bonus points, and a chain of 4 gets 12 bonus points. All of these values were determined by testing, but are not the best ones possible. Lastly, a random value between -2 and 2 is added, which decreases the search time tremendously. As a search algorithm, I used the Negamax algorithm to keep everything simple. Due to the capture being one single move, this was easily possible. Using this algorithm, the bot checks if the game is over, and if not, it stores the current game board, makes the move, runs Negamax on this board, and then undoes the move before proceeding to the next move. Every enhancement for this algorithm is also part of this function seen here, but it's not denoted in the code. It's important to note that this function does not only return the value of the best move, but also the label of this best move, so it can be used outside the function after searching. Therefore, this function returns a pair of an integer and a string. On top of Negamax, the alpha-beta pruning has been implemented, which I guess does not need any further introduction here. To decrease search time, iterative deepening has also been implemented, which step by step searches deeper and deeper until a maximum depth has been reached. After each iteration, the time is checked, and if the search has not yet taken 2.5 seconds, another iteration will be calculated. At the end, the best move for the current board is returned and played. We also make use of transposition tables to store previously seen board states and their evaluation. In my implementation, an entry of this table is a tuple of size 4, which includes the hash value, which is a 64-bit integer, the value of the large search of this board, the depth that was used to find this value, and the best move that was found for this board state. To access an entry in the table, we calculate the modulo between the hash value and the table size to get an index for the array to look at. If there's already an entry at this index, we just override it, meaning we are using a newest first approach. To create the 64-bit hash values, we make use of Zobrist hashing, which can represent every board state combination. We first create 400 random Zobrist number, 4 for each of our hexagons in the 10x10 array. We need 2 values for each player's pieces and 2 values for the blocked state of the tile. Effectively, we are only making use of 320 of those 400 values, as the rest belongs to invalid hexagons and will never be changed. If it's currently player 2's turn at the board state, we invert the whole bit string to differentiate it between player 1's turn. With all of the improvements in place, we can order our moves to even further decrease the search time. In my implementation, the move ordering is first the principal variation, then possible capture moves, then killer moves, transposition table entries, and then all other moves. This has shown to be the fastest way to do it, but that might not be the case for other implementations. Lastly, I have implemented 2 more optimizations out of curiosity. Firstly, the null move with a reduced depth, and secondly, multicut. For multicut, it has been shown that a value of 25 moves and 10 cutoffs is best for the game of Boku and my implementation. But sadly, both optimizations have shown minimal effects, and there are only 30 to 50 additional cutoffs at a search depth of 6. At the very end, I wanted to talk about some features that I wanted to implement, but they either turned out to be too complicated or they slowed down the search process. Firstly, instead of regenerating all possible moves, I wanted to save them in a fixed list in the board class and then just add and remove new moves to this list during the search process. As it turned out, doing it like this is much slower than regenerating the whole list for a given board state, as each move means entering new values and checking for new possible captures. Secondly, I wanted to run for loops in parallel to decrease the calculation time. But that was not only complicated to do in C++, but also didn't speed up the search too much, as most iterations in loops are not independent from each other. Lastly, I wanted to store a vector or a list of entries at each index of the transposition table instead of a single entry. After accessing an index, I would loop through the very short list to find the board's value, or if there's any value at all for a given board. This turned out to be quite complicated and needed more memory, and it didn't really speed up the search by a lot. So these 3 things are not part of my implementation. Now for a quick demonstration of my program. We start up the Boku terminal, and then we can enter the player types. We type H for a human and A for an AI. Then we can choose between a color mode. Usually I use colors, but I noticed that on some computers the way the console text is colored sometimes doesn't work for some machines. So to disable it, you can enter a D, but for this demonstration, I'm going to enable colors. Now we see the ASCII game board, its current evaluation value, and its current hash value. To make a move, we can now just type E5, for example, to place a piece at E5. Then the AI is going to think about it, and it plays F6. We can see here above that it evaluated about 1.3 million positions. It had about 120,000 prunings, and it looked up 250,000 board states in the transposition table. We can also see that there hasn't been found any cutoffs due to the null move, and we had 41 cutoffs due to the multicut optimization. Now it's our turn again, and we can play F5, for example. To show you how to capture, I'm just quickly restarting the game and enter 2 human players, which you can do by entering H twice. We are going to enable colors again and make our moves. As a second player, I can now capture by placing a piece on C3, which I'm entering, and before pressing enter, I'm adding X to mark a capture and the piece I'm going to capture with it, which is D4. So my input for capturing is now C3 x D4. When we press enter, we can see that we have captured it. At the very end of the video, just for you, I'm going to show you two AIs battling it out against each other, but this is not part of the main presentation anymore.